Okay, so any questions about yesterday or any other day? We're clear? So let me just recap a little bit to understand the logic of the last lecture. So we've been discussing the form of correlation functions in conformal field theories. In particular, at the end of the lecture yesterday, we studied the correlator of the two-point function of the energy momentum tensor. This guy plays it's the guy that for sure exists in all conformal field theories. And we saw that the conformal field theory comes endowed with this quantity C that controls the two-point function. Okay? And this C is there in all dimensions. Now we start in 2 dimensions, where things simplify dramatically. If you did the exercise in yesterday's tutorial, you will see that something very special happens to the two-point function of the energy momentum tensor in 2 dimensions. And this C has lots of physical meaning that I'm sure you will learn next week when you study 2-dimensional conformal field theories more systematically. And here I just listed a few. So it controls the things that the physicists would care, like the high energy behavior of the density of states, thermodynamics, something called entanglement entropy. If you don't know what it is, don't worry. And also, what I described at the end of the last lecture, it also is a conformal anomaly. Okay? So it's the coefficient of the conformal anomaly, which is essentially a violation of conformal symmetry that arises from when you couple the conformal field theory to a curved background. Okay? And what we showed around by doing a perturbation around flat space, we saw that indeed, if we just take the form of the correlation function in flat space and do a small perturbation, that we see that the trace of the energy momentum tensor is no longer 0, so that there is an anomaly. Okay? More conceptually, one reason that this quantity is very important is that it defines a monotonic quantity in the space of quantum field theories. Okay? So remember that in the space of quantum field theories, you have all these RG flows, and you want to understand what is the logical relation between different quantum field theories and which quantum field theories can be reached from a given quantum field theory. Okay? And this C quantity is an example of such an organizing principle or lamppost in the space of field theories. So this is this quantity is defined for any conformal field theory. And you can ask what is the relation between, so imagine now you have an energy flow between 2 conformal field theories. You start with a conformal field theory, you perturb by a relevant operator, and it flows in the infrared to a different conformal field theory. You want to know, can we say something about a quantity that distinguishes or relates the 2 theories in the UV and the infrared? And this is precisely the C quantity. So there's a Molozhikov theorem, which is not very hard to prove, but I will not do it here, but it's quite straightforward to prove. Actually, it's in the notes, somewhere in the notes that you have access to. This is precisely the quantity that has this ordering property, that if you have an energy flow from theory 1 to theory 2, that the central charge of the ultraviolet theory is strictly bigger than the central charge of the infrared theory. Okay? So this is extremely useful because it tells you which kind of RG flows are disallowed. For example, it immediately tells you that, you may see this also next week, that you can flow from something that's called a tricritical Ising model to the Ising model in 2 dimensions, but you cannot go backward because C of the Ising model is smaller than the C of the tricritical Ising model. So that's very useful because it is usually these RG flows, as I explained many times, is that these RG flows, even if you have a perturbative description of the theory here, by the time you hit here, the theory is totally non-perturbative. You have no perturbation theory. And in general, you have no real idea what can happen here. But this already tells you a big constraint of what cannot happen there. Yes?
Is there any notion of a smallest central charge?
C equals 0.
Okay.
So the bottom of the mountain is the trivial theory.
All right.
Whatever.
And I can always start from one and
yes.
to another CFT and then
yes.
keep going down.
Yes. Yes. I mean, the intuition is that if you, I mean, think of in Lagrangian terms, you have a whole bunch of fields. You can give them all mass, and then if you give them all mass and you integrate them out, at the infrared you're going to be left with nothing, which is the C equals zero theory. Yeah, that's a good question. Yeah, so there is a bottom. C has to be okay. So one thing that's important is that, yeah, in some sense, unitarity gives a sign to C. So C cannot be negative, because the two-point function of something has to be non-negative in a unitary theory. Yes?
Why does a two-point function be non-negative?
From quantum mechanics, if you look at the two-point function of O and O dagger in a unitary theory, that's a non-negative quantity. You can prove that by inserting a complete set of states, and say that the norm of On mod square has to be positive. Okay, so now one very interesting question is that, okay, this seems very special to 2 dimensions. Can we say something more about other interesting dimensions, in particular 3 dimensions and 4 dimensions? 3 dimensions being particularly important for critical phenomena, and 4 dimensions for applications to particle physics. Okay. There are many ideas about what could happen at scales above the TeV scale, whether maybe the standard model is completed by some CFT. So you want to understand something about flows in 3 dimensions and 4 dimensions. And it turns out that, very remarkably, that, and this is things that have only been understood in recent years. Okay? So that's why I want to mention to them, so that this is not like ancient history, this is really recent history. So let me tell you what the analog of C. There's a horrible tension in notation that originally C was, okay, you'll see what the tension is in a second. But I have to use the notation that is used in the literature so that if you look, you're not confused. So let me tell you what the analog of C is in 3 and 4 dimensions. So in 4 dimensions, where, again, it's only in even dimensions where you can have conformal anomalies just with dimensional analysis, again. Is that at least roughly clear why you can only have conformal anomalies in even dimensions? It's just dimensional analysis, essentially. That the energy momentum tensor has dimension D, and you have to write something on the right-hand side that is covariant, and it has the same dimension. The covariant quantities are Riemann things, Riemann tensors that have dimension 2. So you're never going to be able to write something that has odd dimension, which is covariant. So in 4 dimensions, there's an exercise you can do to write down, and actually this is in the notes. So I've done this before in previous classes. Somehow this year, maybe I went slower, I don't know. There is a way of deriving this, which is in the notes, and that just follows from, and in the 3rd week, you're going to do anomalies, and maybe either Dan or me, I can come and explain how this arises from a more abstract point of view in the study of anomaly. But the point is that in 4 dimensions, there are 2 possible structures that can appear, that have the right dimension, and that are physical, is a coefficient that multiplies the Wild tensor. Do people know what the Wild tensor is? It's a kind of the traceless part of the Riemann tensor, the Wild tensor square. And then there is A that multiplies the Euler density. Okay? This is a topological invariant. Now, the quantity that has this nice property is not C, unfortunately, it's A. Okay? So A is a quantity that has the property that AUV is bigger than AIR. And this was only proven very recently. I mean, the conjecture was for a long time, but only recently there is some argument that this is indeed the case. Okay. Unfortunately, technically, if you want to understand, if you want to read off A from a flat, if you're a flat space person, you want to read A, it's not enough to study the 2-point function. You have to study the 3-point function. So A is measured by the 3-point function in flat space. So if you were very motivated, you could do the generalization of the exercise that I proposed yesterday of looking at the most general 2-point function, apply conservation, blah, blah, blah. If you did that, at the end of the day, you will find that there is one structure that's precisely, that would define, the coefficient of that structure would define A. Good. And in 3 dimensions, there is no conformal anomaly. So you could say, for a very long time, this was at okay, so this is very unsatisfactory. we don't have a quantity that can organize RG flows. And through the study of esoteric things like supersymmetric partition functions on spheres and also ADS-CFT, it was found that there is a natural candidate of a quantity that's called F. Every dimension has a different name, which is very, very annoying. So you have C, A, and F that has this property, okay? And you could say all of them look completely different. I mean, it looks random, but there is one way of, there is one observable that you can define in all dimensions that always measures the right quantity. So that in 2 dimensions measures, in the 2 dimensions measures C, in 3 dimensions measures F, and in 4 dimensions measure A, okay? And I'm just telling you the answer. You can, if you're motivated, you can try to understand why this is true in 2 and 4 dimensions. The quantity that measures the parameter that is monotonic energy flows is the study of the partition function of the conformal field theory on the corresponding d-dimensional sphere. Okay. So if you can put your conformal field theory on a sphere. The sphere is conformally flat. So if you have a conformal field theory in flat space, you can conformally map it to the sphere. This is nice because the conformal field theory on a sphere, the sphere is a compact manifold. So this observable will be infrared finite. We have very well nice and defined observable in the infrared. And now you can try to resolve the physical part of the partition function in d dimensions. And the physical part of the partition function in d dimensions is exactly R, F, and A in 2, 3, and 4 dimensions. So just to give you a hint, if you want to check, how would you read C and A in even dimensions? The way you would read it is that you can use the definition of the energy momentum tensor. So you put the theory on the sphere, okay? And you ask, what happens to the partition function? So this is in even dimensions now, so where you have conformal anomaly. So I look at the variation of the logarithm of the partition function when I want to change my radius. So I change my radius from R to R plus delta R, okay? Now, if this was a really conformal field theory and there were no conformal anomalies, the answer should not depend on R. But what is this? This induces a change in the metric, right? So the metric is R squared times the metric. How do I want to write this? Okay, so let me be more concrete. So let's write the metric. You can write the metric on the sphere using a stereographic coordinate. Okay? That's the statement that the metric is conformally flat. The metric has some overall factor times the metric of flat space. And since the conformal field theory does not depend on the overall scale, I can just place my CFT canonically on the sphere. Now I want to study what happens if I change delta R. If I change a small change in the radius of the sphere. This will induce a change in the metric, which we can compute very easily from here. I just plug here R plus dr, and I compute to linearized order in R. So this will induce a change in the metric, delta G mu nu, which is 2 delta R over R G mu nu. Are people happy with this? I just plugged in here R plus delta R. So you get the term that's proportional to delta R is 8R delta R. I divide and multiply by R squared, and you get this, okay? Good. But now we can go back to this computation. So I want to see what happened to the partition function, which is a function of the metric, right? I integrated all the fields, so now the partition function depends on the background field that I couple my theory to, the metric. But this, by definition, is the integral over space of T mu nu delta G mu nu. A change in the metric defines the energy momentum tensor, okay? But what did I do? I know what delta G mu nu is. I changed my radius, and it's a homogeneous change, okay? So from here I get that, okay, forget about factors of order 1. So I get here delta R over R dx square root of g, and now I take the trace, right? It's proportional to g mu nu. So here I'm just going to trace the trace of the energy momentum tensor. But now I can use the formula for the conformal anomaly. So in 2 dimensions, just to be concrete, what we're going to get is that delta log z is proportional to c, which was the coefficient. Where do I have this? Somewhere. Remember that in 2 dimensions, T mu mu was c times r. Okay? So what I have is c delta r over r, the integral dx square root of g r, integrated over the sphere, say in 2 dimensions. But this guy, what is this? This is just 1. Okay, in some normalization, this is just 1. It's the Euler number of the sphere, which is, okay, it's 2, but okay, we're not caring about things of order 1. So this tells you that this goes like c delta r over r, which means that indeed the sphere partition function, the 2-sphere partition function, measures c as the coefficient that appears in the exponent of the anomalous radius dependence of the partition function. If you do it the same thing in 4 dimensions, here you're going to get the integral over the Euler density, which is non-zero on the sphere. Okay, and what would okay, but notice that in 4 dimensions we have 2 terms, Weil square and Euler. What would be the integral of? So if you do this analysis, you're going to get here the integral over the sphere of Euler plus Weil. What happens to the integral over Weil over the first sphere?
Was it treated as
You told me that you know what the Weil tensor is. So if you integrate the Weil tensor square over, okay, or if you evaluate the Weil tensor in the sphere, what do you get?
I never integrated.
No, you don't have to integrate. No, it's actually you don't have to integrate to get to the answer I want you to tell me. So what is the physical characteristic of the Weil tensor?
It has the same symmetry as the Riemann tensor, but when you take the trace that we
Yeah, this is okay. This is the mechanical way. This is the definition, if you wish. Yeah. But the thing that's special about space-times that have a vanishing Weil tensor, these are the ones that are conformally flat.
Okay.
A manifold is conformally flat, even only if the Weil tensor vanishes. So that means that when I do this game here, the Weil square term will drop out, and I fish A, not C. Okay. So if I did the same exercise here in 4 dimensions, you would get the ZS4. And in 3 dimensions, there are no conformal anomalies. But if you study now what is the physical, which means regulator-independent part of the 3-sphere partition function, there is the finite part of the partition function is a scheme-independent, which means that it's physical. And that's precisely what defines F. So this was in 2. This was in 4. And in 3, if you look at the finite part of the 3-sphere partition function, which is universal, it means that it doesn't depend on any UV garbage, just an intrinsic property of the conformal field theory. This defines this quantity F that has the monotonic property. Okay? So you see that by doing something that a priori you may not want to do, which is to study, we care about flat space usually. But the thing that's nice about this story is that by putting the theory, by being flexible and studying the theory in a different geometry, you can identify observables that we care about in flat space, like A, C, and F. Okay, so that's why I wanted to tell you about this, because this is important and also recent. So in the rest of the lecture, what I want to do is finish, if you wish, the analysis of correlation functions in conformal field theory and show you that a truly remarkable property of conformal field theories that we will see. Okay, I don't want to spoil it because what's the fun? Okay, so what we saw in the previous lectures is that the 2 and 3 point functions in a conformal field theory, define certain data. So the two-point functions, if you remember, define the scaling dimensions. This was the exponent in the two-point function. And more precisely also the spin. I mean, the operators have a dimension and a spin. Okay? And the three-point functions define some structure constants, Gi, Jk. Remember that the position dependence was completely fixed by conformal symmetry. Okay? We also saw that for n bigger than or equal to 4-point functions, things didn't look as simple anymore because now we had a conformal invariant cross ratio, so we had arbitrary functions that can appear in the general form of the correlator. So you would naively think that you have to provide extra data for every time for the 4-point function, for the 5-point function, and so on. Okay? So let me, for concreteness, let's look at the 4-point function, which is the main guy we will study. And we'll look at the 4-point function of scalar operators, scalar primary operator. So this is something that also we saw. We can get an arbitrary function of the two cross ratios that we can define given 4 points. And then this was just fixed the dimensional analysis by scaling symmetry. And just to hammer it, the cross ratios is 1, x1, 2 square, x3, 4 square, x1, 3 square, x2, 4 square, and v is x1, 4 square, x2, 3 square, and the denominator is the same. So the goal of this lecture is to demonstrate that this G is not a new independent quantity. G will be written in terms of the data that appears in the 2- and 3-point function. So philosophically, we will tell us that everything is determined by the 2- and 3-point functions. So let's start the analysis. Okay? So the goal, in some sense, is to arrive at the statement that the conformal field theory is completely characterized by the following data: the dimensions and the spins of the local operators and the structure constant.
Just by seeing the argument for 4-point function, we'll be able to conclude.
Yes, you will see why. If it's true for 5-point function, and I'll say something even stronger. So, actually, the 4-point function is extremely useful in the following sense. So, there are two statements that I want to transmit today. So, one is that the 4-point function does not carry new data, but actually, the consistency of the 4-point function, and there's something that we're going to discuss, which is called the OPE, will impose very strong constraints on the type of data that the CFT can have. So at this point, you could say, I can give an arbitrary list of numbers here, and this is a good CFT. The point is that no. So consistency of the 4-point function will put huge constraints on this, okay? And that's what we want to study. Okay, so this is, so let me just write it. Imposes constraints. On CFT data. So you could ask, why are 5-point functions, 6-point functions give extra constraints? And the answer is no. And I think by the end of the lecture, or at least by the end of the homework, when you play with it a little bit, you can convince yourself by drawing pictures why looking at higher point functions do not give you new constraints beyond those of the 4-point function. So if you impose this constraint, you're done. So now, from this point of view, the game that we want to play essentially is a classification of the allowed CFT data, so classification of dimensions and spins and the structural constant. Okay? You could think that follow from the constraints that are imposed by the 4-point function, which is called crossing symmetry. So if you wish, the classification of CFTs is the classification of this quantity. And this is kind of a generalization. You can think of it as an analog of classifying Lie algebra. What are the possible Lie algebras? Well, here you have some data that also looks a little bit like Lie algebra. You want to see what are the possible CFT data that are consistent. Okay, so now let's get cooking. So again, let's consider a 4-point function of identical particles, identical operators. So we'll start with an elementary observation that will be important for us later. Okay, so. And again, just for notational simplicity, I'm taking all the operators to be the same. Okay. Now, see, these are 4 identical operators. So just by Bose symmetry, it means that the answer should be invariant if I exchange 1 and 3. The correlator is totally symmetric under the permutation of any of the positions of these guys. But now we can study what this means at level of the equation. So it means that, tell me if you want me to do it in more detail, but what you can see is that if I exchange 1 and 3, I exchange U with B. Do you see that? Okay. And if you look at these prefactors and see what happens under U and under U exchange with 3, you will find so you'll find the following equation. Okay. So this guy was just a statement that under U goes under 1 exchange with 3, U gets exchanged with V, and then you just have to take care of these prefactors. And the change can be absorbed into these cross ratios. Okay? So far, this is a trivial relation. This just followed from a trivial symmetry, which is Bose symmetry. Okay? But we will see that this will lead to all the important constraints that we're looking for. Okay? Okay, so what is now? So far, all that we've done until now is if you wish, kinematic. Now we're going to use the main dynamical assumption in well, it's not an assumption. You can prove that this is a property of conformal field theories, which is we're going to use the operator product expansion. So. To analyze the 4-point function. And you can use the same logic to analyze any n-point function. Okay? So what we do is that we consider 2 arbitrary operators, OI, OJ. Okay? And there are 2 different points. Okay? And now we look at, if I'm an observer far away, I'm doing kind of the idea of the OPE is very intuitive. So I have 2 operators, but if I look from very far away, I cannot really distinguish these 2 operators from a local operator. This is like doing like a multiple expansion. If you're very far away and you have 2 charges, all that you can see is that you have something localized that has a dipole moment, a quadrupole moment, and so on. Okay? More technically, what it means is the following, is that you take these 2 points, you draw a sphere around them that surrounds both of them, and no one else. So there can be operators outside the sphere in general, right? Okay. And the notion of the OPE is the statement that I can represent these 2 guys as an arbitrary sum of operators. Okay? So I sum over all possible operators. Like that. This is the analog of the multiple expansion. And this guy, of course, is a function. Okay, we'll see what is a function of. Okay. So this is the multiple expansion that you can do in field theory. More concretely in equations, it means that if I take OI, let me write it a bit more formally, OI at x1, OJ at x2, can be replaced as the sum over all operators in your theory that are labeled by k. So k is a big index label, a function of the initial operators and k that labels all the operators I'm summing over, which is going to be a function of x1, 2, the difference of 1 minus 2, that's just translational invariance. Some derivative 2, which I'll explain in a second, times OK evaluated at x2. Okay? So if this guy was at x1, this guy was at x2, I can put this guy at x2. It turns out that it doesn't matter where you put it. You can put it anywhere on the sphere. This will only change this function by translational invariance, essentially. Okay? Now, I have to explain why this derivative is there. So essentially what I'm doing here is I'm summing over all operators in a conformal field theory. I already explained that operators in a conformal field theory are either primary or descendant. The descendants are derivatives of primaries. So what this sum does is sum over all primaries in the conformal field theory, and this derivatives is summing over all the descendants. Okay. Good. Is there any questions about this? What the basic idea of the OPE is? I think it's quite intuitive. And this expansion can be used inside any correlation function. So if I'm looking at a correlation function, or ix1, or jx2, and here I have whatever operators I like, as long as the positions of these operators lie outside the sphere, I can use this expansion. Okay? And in fact, anyway, yeah. For conformal field theories, this expansion is absolutely convergent. That's why it's extremely powerful. It's an absolutely convergent expansion. Now, we can use now conformal invariance to restrict the kind of functions that can appear here. Because the left-hand side should transform the same as the right-hand side under conformal transformation. So let's see that the constraints that Lorentz generators and dilatations give you, it tells you that this Fijk is a function of x and derivatives is x of delta. Let me write it and then you tell me why this is correct. So this is proportional. Okay. So, okay, so the reason that F takes this very particular form is precisely scale invariance, right? Because this guy should have a certain scaling weight and should match the scaling weight of here, okay? So that's why it's exactly the same reason why the three-point function had a very particular dependence on x. It's exactly the same. So this is just fixed by scale invariance. And also here, every x, so this already has the right dimension, right? So that means that every x that can appear should be multiplied by a derivative. So this guy is dimensionless. And the reason that all indices are contracted in a proper way is just Lorentz invariant, or rotational invariant. Okay? But so far, this doesn't fix these numbers, alpha, beta, and gamma, and so on. Okay? This goes on forever. This only tells you essentially dimensional analysis, and that's it. Okay? Now, to find the coefficients in this OPE expansion, what we can do is act with k mu. Okay? Now, this will have some teeth because k mu is, you remember, the transformation of primary operators under conformal transformations. It is a non-trivial thing. So now what I can do is I can act with k mu here. Okay? We know how OI and OJ transforms under k transformation. And now I act with k here. Okay? And I compare term by term. And in this way, you obtain alpha, beta, gamma. The point of so I'm not showing the details of how to do this. It's straightforward, but tedious to do. But the main message here is that all coefficients are fixed by conformal symmetry. Okay, so all the coefficients here up to the normalization factor that we'll discuss in a moment, this function here is completely fixed by conformal symmetry. Okay.
See that by applying the special conformal transformation.
Yes. I'll show now maybe a simpler way. In practice, that's, I think, the simpler way to do it. But I just wanted to use this logic because that's the logic I use for this. A simpler way to see that this coefficient is fixed completely by symmetry is that let's look at the three-point function that we already derived the word identities for. So the three-point function took this form. Now what I can do is okay, so we know what the answer for this guy was, right? Cijk, and some denominators that I'm not going to bother to write, but this was x12 to some power, x23 to some power, x13 to some power. So that's just the direct consequence of the word identity. Now I can do the OPE between these two guys. This will give me something like Fijk prime of x12 delta k times the two-point function, right? So I'm replacing this OPE into here. So I'm removing these two operators and replacing it by one. So here I'm going to get the two-point function of O k prime at x2, O k at x3. But we also know what this guy is. This guy is essentially delta k prime divided by x2 minus x3 to the 2 delta k, right? So now I can compute this coefficient essentially by expanding. Now I can expand both sides. In x12, so x12 is the thing that in some sense we have small. We're doing the OPE of two operators that are close by. Actually, they don't have to really be close by, but x12. Actually, what's important is that this is smaller than x23. Okay, so we expand in this. And then you compare term by term. This is completely straightforward to do, even though you're taking derivatives is painful, but it's completely straightforward to do a Taylor expansion of this guy. And here, and you compare term by term, and this completely fixes. This is just to tell you in a way, in a language that maybe it's more intuitive, that all these numbers are completely fixed because the x dependence here is completely fixed. And here I get the coefficients I'm trying to figure out. So obviously the coefficients are completely fixed in terms of the data that I had here, okay? And notice that this, so something that you can try to understand by playing with this equation is to understand that this OPE expansion is convergent with a convergent radius which is the location of the next operator. So I have two operators, and then I have whatever number of operators far away. The radius of conversion of the expansion is to the next operator. Okay? And you can prove this explicitly in this example. You can show that this expansion in a small x1, x2 is convergent as long as x23 is bigger than x12, which means that x3 is farther away than x2. Okay? Very good. So this can, so there is some games one can play here, and one can write down this fairly explicitly. It's not very illuminating. But the key point for us is that everything is fixed by symmetry. Again, there is no unknown quantity yet. Okay? Oh, but something that's very important here is that here I didn't tell you what the coefficient here was. I told you that up to an overall coefficient, we know the x-dependent, okay? But now by doing this comparison, what we figure out is yet another important thing, that the tensor that appears there, Fijk, is it's proportional toCijk, which is the coefficient of the three-point function. Okay? So we see that the data, that the OPE expansion contains precisely the data that we already had, which is the dimensions and the three-point function coefficient. This is starting to smell a little bit like the four-point function so far seems to have no new data that's not fixed by symmetry other than we already had before. Because everything is fixed in terms of in terms of the C's and the dimension. Okay, so now what's the strategy of this? So what you can try to do is the following. So now we're interested in computing a correlation function. In particular, the four-point function, but whatever I will say will apply to any n-point function. So how would you do it now? So let's go back to the guy that we're doing as the toy model to minimize indices and stuff, but the logic is exactly the same. Now we want to compute this guy. We know nothing about it a priori, but now we introduce this notion of the OPE, which allows us to replace two operators by two other ones. So now I can imagine, I can imagine doing the following. I can do two sequential OPEs. I can do the OPE of these two guys, of 1, 2, and separately the OPE of 3, 4. Okay? So what I will do, I'll just say it in words and then I'll write some formulas because once the formulas will start becoming long. But I think the idea is very simple. So you do the OPE here and the OPE here. Okay? So this is going to be replaced by a sum of operators. This guy is going to be replaced by the sum of operators. So I have reduced the four-point function to a sum of two-point functions. Okay? But again, the two-point functions are completely fixed by, in terms of the dimension. Okay? So I actually have an algorithmic way to take, notice that the logic didn't depend on this being 4. It could be 75-point function, and you could do it sequentially. You reduce the n-point function to essentially data that you already have, essentially the OPE data that knows about the three-point function and two-point function. And do you have the courage to write this? Okay, I'll do it once so that. So we'll write in more detail what I said in words now in a formula so that it doesn't look abstract. It shouldn't be abstract. The thing that's important is that in the OPE, we have to sum here over all operators, okay? All operators that can appear in the OPE of two operators. Of course, there are selection rules. So if you have an operator that has a certain symmetry, it may or may not appear. I mean, there are selection rules that tell you which operators can appear on the right-hand side just fixed by symmetry. So if you have something that's, for example, odd and even cannot appear on either side. It has to preserve like usual, nothing fancy, just usual symmetries like that. So here I'm summing over operators O that flow in the decomposition of this guy, and O prime are the operators that flow into the decomposition of 3 and 4. And now I just use this. So I have C phi phi O, C phi phi O prime. So this comes from here. This comes from here. This comes from the fact that we fixed that the normalization of the OPE is precisely fixed in terms of C, which are the coefficients of the three-point functions. And then I can write, why do I have an index A here? Yes. Yeah, so because, okay, so Because now I'm being a bit more explicit at the risk of formulas looking a bit more messy. Okay, so these are again just the OPE coefficients. Now, why do I have an A? Because here I should really be more careful, or depends how explicit you want to be. When I sum here over the OPE, I have to include operators of any spin. Okay, so this A labels the spin of the operator that you get in the OPE. So this is the spin of the operator that would flow in this channel, and the spin B will be the spin that flows in this channel. And then I get the two-point function. Sorry, x2 and x4. But again, so we reduce, this is what I said in Word before, we reduce the 4-point function to the 2-point function of the guys that flow, okay? But this we already know. This is just some tensor, IAV of x2 minus x4. We can diagonalize the space of operators. Okay, this should be O prime, I guess. Divided by x24 to the 2 delta O, okay? And this tensor IA is completely fixed by conformal symmetry. Remember that we worked it out for vector and for the energy momentum tensor. This guy was written in terms of this inversion tensor. It's a completely explicit tensor that we know. Yes.
Are you assuming that like all local operators are degenerate in their scaling dimensions?
No. Why degenerate?
Because
I'm summing over all. When I mean summing over O, I'm summing over all operators of all dimensions.
yeah, but there you're writing delta O prime, but in principle the correlation function of two different operators doesn't need to vanish. It only needs to vanish if they have different delta.
Yes, but so let's look at the space of operators. So if they have different delta, they just vanish by conformal. If they have the same delta, I can just diagonalize that metric. I can go to an orthogonal basis. That's all I'm doing. I have a matrix of two-point function. I can diagonalize. It's like diagonalizing the metric. If you want to have a non-diagonal, if you want to choose in a different basis that's not diagonal, put here a metric. It doesn't matter. Put G, O prime. All I'm doing is that.
Who says its diagonalization is the identity? Because that's what you're assuming here. You don't have a coefficient. No. So you're talking about the normalization. I can always. Are you worried about the normalization of the two-point function? I can normalize the operator of all operators to be 1, except for the energy momentum tensor. Okay. So now I can write this in this way. So notice that I get this guy 555 O squared, one from here, one from here. And then I define this quantity that will plays an important role in this business. Okay? And you can read, okay, I'll write it so that you don't complain. Delta O LO of xi, I can write in terms of what I wrote before. So it's S12 to delta phi, X34 to delta phi, CA X12, D2, C B X34, D4, acting on this two-point function. Okay. Good. But now what we know is we can look at the formula that I had somewhere there. We knew from conformal invariance that the 4-point function was given like that, okay? But of course, we didn't know what G was. Now what I've done is write G in terms of 2- and 3-point function, okay? So by comparing this with the computation we've done using DOP here, we arrive at the following relation. We have the GUV, which is the object that symmetry alone didn't tell us anything about. We just knew that there was a function of the cross ratios. Now we can write that function of the cross ratios in terms of things that we know, or that data, that input data that we had from the 2 and the 3-point functions. So this, okay, so what is this? Is it clear what I did here? I just equated the abstract formula given in terms of conformal invariant to the formula that you get when you apply the OPE to the 4-point function. Now, what are these things? So these guys have a name. These are called conformal blocks. Okay? And have the good property, as it follows from the analysis that we've been doing, that are completely fixed. By conformal symmetry. So this is like group theory. This factor is just a group theory factor. Okay? In fact, there's a very precise analogy you can make with things you've seen before. This guy sometimes is called a conformal partial wave decomposition of the amplitude. So you take your amplitude, 4-point function, and you decompose it into some basis of partial waves. Okay? This is exactly what you do when you have a symmetry. So if you study, for example, scattering, non-relativistic scattering of a spherically symmetric potential, you can also write down your amplitude and decompose it into a spherical harmonic. And all the physics is in the coefficients of the spherical harmonics. Okay? And in a very precise sense, conformal blocks are the harmonics, not for the rotation group, but for the conformal group, for SO d plus 1, 1. Okay? So these are things that are just dictated by symmetry. Okay? Now, the form of these guys can be nasty. They're quite nasty, in fact. So for even dimensions, there is a closed form. For the even, there is a closed form analytic form that you can write down for these conformal blocks that, with a lot of work, you can derive given from this definition. This was done by Dolan and Osborne. This was quite a heroic thing they did to realize that this mess could be organized into a product of hypergeometric functions. So now you understand why I didn't want to derive the coefficient, because this is just messy. But what's important for us conceptually is that this is something that someone in a different galaxy that was studying conformal symmetry would discover, because it's completely fixed by symmetry. There is no dynamics here. And for the odd, they're known, but not in a name of a function that you would recognize. But there are various ways of computing them explicitly, and people put this in the computer when they do the conformal bootstrap, which I'll describe soon. Okay. Is everything clear until, oh, here, so someone should have, what's missing here? Square, because I applied the OPE twice, so I have one from 1.2 and one from 3.4. This will turn out to be important because C square is positive. Okay? So yeah, so when you study positivity constraints, this will be important, the fact that it's positive. Okay. So yes.
We should get the same result if we just reduce like 2 operators and then use the 3-point function. Should be, right?
Yes, you're right. Yes. Yes. But now you have to do the 3-point function with arbitrary numbers of descendants and stuff. Right? Because the OPE will include the descendant. No, I think, yeah, you can do it that way. And in fact, you can do it in a different way. So, and that's where the big constraint will come from. So let me keep this formula because it will be important. So in what other way could I have computed the 4-point function? Can someone like give me a guess? I mean,
you could have just contracted other things than 1 with 2.
Exactly, exactly. And the physics should not depend on in which order I apply the OPE. The OPE is an associative transformation, so I could apply it in order I like. So then this leads to the important idea of crossing symmetry. So this tells us that breaking that phi x1, phi x2, phi x3, phi x4. So I computed it there by doing the OPE like this. But this should give me the same as if I have done the OPE by contracting 1 and 4 and 2 and 3. Since I'm looking at the 4-point function of identical operators, actually, for any case, what I say is true for any case, but this equation is the one that gives very strong constraints on the data, because it tells you that one way of computing the partition function that depends on C's and deltas has to equal to a completely different way of computing C's and deltas, okay? So in equations, one way that we write this, because formulas, you see, are getting longer, so there's a pictorial way of representing what we mean by the crossing symmetry equation, is that we do the OPE. Now, I should warn you that this should not be thought of in any way, shape, or form as Feynman diagram, okay? This has nothing to do with Feynman diagrams. This is just a statement that I'm fusing 1, 2, and 3, 4, and I have a complete set of states flowing in the middle. This should equal, okay, in general, imagine that 1, 2, 3, 4 were different operators. Here in general, different representations could flow depending on the quantum numbers of 1, 2, 3, 4. If all of them are the same, of course, the states that can propagate in one channel and the other are the same. But if the quantum numbers are different, they need not be the same. 2, 3. But all that I did here essentially is swap 1 with 3, okay? In this OPE. So, but we knew what swapping 1 and 3 does to this function G. Remember that before this was just a trivial statement of Bose symmetry, okay? But now this will be non-trivial because the OPE, so in this analysis of Bose symmetry, all operators were treated symmetrically. But when we do the OPE, we're not treating things symmetrically, right? We choose 2 and 2, right? So now this equation will have interesting consequences, okay? So let me write this equation. And I'll be done. I want to try it, really exhausted, so. So here I just exchange 1 and 3. So now I just want to write this equation using the conformal block decomposition. Okay? So that means that I'll write it in the way that slightly different way that I wrote it there. Oh, no, there is no 2, I think. No, there is no 2. Right. Concretely, what this means is that, and now I'm looking at a very particular case with the 4 operators, that O is the same as O prime. All the operators in the fusion channel are the same because I'm just doing the P of the same operator. You get the C phi phi O squared times B delta phi times the conformal block of intermediate states with summation delta O and spin LO evaluated at UV minus U delta phi of that G, the conformal block of dimension O in LO is GU. this has to vanish. This is an absolutely non-trivial equation. I mean, this. So there are 6 squares here, and the dimensions here are built all over the damn place. Okay. So what this does is put constraints admissible CFT data. So if someone hands you, someone thinks, oh, I have a conformal field theory, here is my conformal field theory data. Well, if it doesn't pass this, you should say go home and try again. And actually, the point is, one very important point about this is that the space of CFT data that is consistent, which means that obeys the Gaussian symmetry, is incredibly sparse. Namely because I can have anything I want, but actually that's not true. It's incredibly sparse. There's only very few correlated values of deltas and c's that are solutions of the Gaussian symmetry. This has a physical interpretation of universality. That there are many systems in the ultraviolet that flow to a handful of CFTs in the infrared. I should say that it is a conjecture that above, so for D equal to 3, it is believed that crossing symmetry constraint is all there is. So are all the constraints. And one thing that you can check is it's a fun game of drawing a picture. You could convince yourself, take the 5-point function. I mean, try to show the following. We're just drawing pictures. You don't have to write any formula. We're just drawing pictures. Try to show that the associativity of the OPE in the 5-point function follows from the associativity of the OPE of the 4-point function. So, is it clear what is working? That if you have crossing symmetry of the 4-point function, you can use this in the building block of the 5-point function to decompose the 5-point function in any channel that you like. So this gives no new constraint. No new constraint. Now, the reason I'm saying this is a conjecture is that, okay, so the reason I'm saying this is a conjecture, even though I think it's very clear that this is true, is that in 2 dimensions, it turns out that, and hopefully you'll discuss this next week, in 2 dimensions, crossing symmetry of the 4-point function, or namely, another way of writing this is, crossing symmetry is not enough. You have to apply extra consistency conditions that are required for the conformal field theory to be consistent. And hopefully you'll study this. You have to, in particular, show that the theory is modular invariant. And I'm sure you will see some of that next week. But about 3 dimensions, it's really believed that there is no new constraint other than the 4-point function. So sometimes this idea of kind of quote-unquote solving conformal field theory by using this crossing symmetry, it's called, this logic, it's called as the name of conformal bootstrap. So I'm just writing the buzzword in case you come across with it. And it's kind of a very beautiful and simple idea because it tells us that all that you're really using here is very, notice that the word Lagrangian didn't appear anywhere in the entire discussion. All that you're using is that you have an operator algebra, and that is despite certain associativity to OPE. Okay. And the idea that from these constraints alone, we should be able, if we're smart enough, we should be able to determine solve the theory. Now, I should say that this has only been accomplished in a spectacular way, in a rather big generality, in 2 dimensions, 2 space-time dimensions. So this idea of the bootstrap was, revolutionized the way we think about 2-dimensional critical phenomena. Critical phenomena in 2 dimensions. Because in that case, as you will see next week, a conformal symmetry in 2 dimensions is not, I already mentioned it during the class before, but the conformal symmetry in 2 dimensions is not finite dimensional, it's infinite dimensional. So this gives extra constraint on the dynamics. And in 2 dimensions, essentially, this idea of the crossing symmetry led to a purely algebraic solution to the critical exponents and of the coefficients and critical of the coefficients of an infinite number of critical behaviors. So this is someone who, by pure thought, wrote down once and for all, just using consistency, all the possible critical exponents that a conformal symmetry can have in 2 dimensions. Here I'm focusing on something that C was the guy that I talked before at the beginning of the class, where C is less than 1. Okay? For C less than 1, everything is completely characterized and completely classified. So just as you know now all of a sudden a solution of an infinite number of critical points, of an infinite number of lattice systems that are complicated and so on, that you don't know how to compute the critical exponent. This solves it for you in one shot. For example, you have, by doing this, for the 2-dimensionalizing model, of course, this one can be solved was solved in the lattice before using this fancy CFT, but many other ones that you know was first solved by using CFT techniques. You can compute the exact dimension of the spin operator to be 1/8, and the exact dimension of the energy operator to be 1. But okay, so this was done roughly in the 80s. I don't know, but I'm not sure you were born back then. But no. I was born. I'm not telling you how much before that. Okay, so, but this problem of using Bootstrap for higher dimensions was essentially stuck for many years until recently. There was kind of a breakthrough that that led, in particular, to so people have studied this equation in 3 dimensions. Unfortunately, okay, you have to study this equation numerically. Okay? And try to put constraints on what is the consistent data. But essentially, by studying this equation in 3 dimensions in a clever way, and numerically, people have determined with world record precision the critical exponents and OPE coefficients of a system that we really care about, the 3-dimensionalizing model. Again, this is the guy that describes the universality class of magnetism, the critical point of water, anything. And remember, this is the guy that had the UV realization as, say, lambda phi to the 4, or as an Ising-Hamiltonian lattice. And people before computed these critical exponents using this epsilon expansion, which is not controlled, or using Monte Carlo. Or using this bootstrap, the critical exponents were measured to incredible precision, something like 6 or 7 decimals, way better than Monte Carlo can do at the moment. And for example, computed the dimension of the 2 relevant operators of the Ising model. So this goes for, I don't know, 5 or 6 decimals. So this is the dimension of the spin operator, this is the dimension of the energy operator. And actually, there is kind of much more. There are many more operators that the Ising CFT has an infinite number of operators. And there's a lot of information about the full spectrum of the theory in particular. But this is quite remarkable. This is a way of solving the critical system just by using consistency conditions, not using anything else. So that's essentially all I wanted to say. One thing that would be very nice, and I'm not leaving it as a homework because I myself don't know how to do it, but one thing that would be very nice, and that hasn't really been yet accomplished, is to have a more analytic understanding of how to study these equations above 2 dimensions, so that you don't have to rely on linear programming, whatever it is, to solve the equation. So with that, I'll stop it. Okay, so if you want to ask me questions, my office is for 27.